So we've managed to define a curvature for a surface embedded in space-time. So here is our surface sigma, which has some structure on it. Now we've got a metric, h, we've got a second fundamental form, k, and we have the notion of derivative, which I'll call 3del. And we concluded that there was a curvature on this surface, which we'll call 3r, which we defined to be 3 del A, 3 del B, minus 3 del B, 3 del A, which when acting on an arbitrary vector field in the surface gives you 3 R A B C D V D B C N C is equal to 0, so that the thing is entirely in the surface. So the next sort of result that would be useful is somehow to relate this curvature to the curvature of the ambient space-time, which remember has got a metric g, a covariant derivative, and its own curvature r. This calculation is a bit of a mess, but nevertheless is useful to see how it works in many areas of general relativity and cosmology and the like, so we will simply proceed and do it. So the starting point is to look at this thing. 3 del A is going to act on a tensor with two indices b and c. So if you think about that, what you do is you project all of the indices of the thing that you're trying to take the covariant derivative of. And then what you would do is you'd have 3 del Q V R here. So that's the first term. So that's this thing here. And then what you would do is, of course, subtract off the same thing with A and B swapped round. So I will just always write like that to make life easy for ourselves. Then you need to do the same thing with this 3 del. And what will happen to you is that this is going to give you H A P, H B Q, H C R del P. And at this point you're likely to start running out of letters if you're not careful. H Q X H R Y dx, and then this just acts on Vy. Then you subtract off the same thing with A and B swapped round. Now about the only thing you can do is to substitute in your form for H in terms of the metric and the unit normal vector. So if you do this, you see you'll get a long looking mess. So you have a GQX minus or plus NQNX, that's HQX, times the same thing with an HRY. And then that's on del X Vy. And then you subtract off the same thing with A and B. Then you multiply it out. Like many of these things, it's not so hard once you know how to do it. But the first time is a little intimidating. So multiplying out these two brackets, I'm going to get 4 terms, which are, well, let's see. I'm going to look at, first of all, the derivatives of these things separately. So I just want to look at what I get from there. So it will be GQXGRY minus or plus. So that's that term with that one. Then there's this one, NQNXGYR minus or plus that one with that one. That's GQXNRNY. And then plus the thing with 4 n's, and we can close that bracket. So that's one collection of stuff in which this derivative acts on these things. But then there's another one where you have a second derivative of this vector field, and you don't want to forget that. But in actual fact, it's easier not to expand this out. Just get it from here. So that will be HAP, HBQ, HCR, HXQ, HRY. That's it, del P, del X, Vy. And then you subtract off the same thing with A and B swapped round. Now things start to simplify. The covariant derivative of metrics is always equal to 0, so we can forget that term. Now we want to look at this term here. You have an NQ here. If you do not differentiate this NQ, it will come out and hit this H and give you 0. So the only term that will survive is what happens when you do take the derivative of this thing. Nothing else will survive from these three things, because if you take the derivative of the metric, you get nothing. If you take the derivative of this nx, you'll have an nq that is sitting outside that's bare, will hit this hqb, so you get nothing. So you had better differentiate it. But now, you see, you have a GYR nx, which you can take outside. GYR commutes with covariant derivative and just simply acts on this thing, gives you HCY. So the first term here that survives is HCY nx del P of NQ. Times del X Vy. So that's the first non-trivial term. But you can now make the same argument on the next term. Here, del acting on G gives me nothing. Del acting on del acting on NY will leave me an NR. An NR will come outside this bracket and hit this HRC, and of course I'll get absolutely nothing. So the only term that will survive is one where I differentiate this N. So you will end up with, we missed a plus or minus sign here. GXQ comes out and turns the HBQ into HBX. So you have HAP, HBQ, GXQ, so that's HBX, HCR. Then you have an NY which comes out. And then you have a del P of NR. And that's multiplied by del X of Vy. Then you've got this term here, NQ, NX, NR, NY. Taking out either the NQ or the NR will hit either that or that, but you've got two of these, you can't differentiate both of them, so this term will automatically give you 0. So all of these vanished because either del G is equal to 0, or because HABNA is equal to 0. Then there is this final term here with 5 h's sitting in front of it. H is a projection operator, so HQB, HQX is of course just the same thing as HBX. HCR, HYR is the same thing as HCY, so that simplifies life a little bit. So you end up with plus HAP, about which you can do nothing. HBQHQX is HBX. HCR HRY is HCY. Then you have del P, del X, Vy. And then you subtract off the same lot of stuff with A and B swapped round. So that's the first step. Now what you see is that, of course, you've got things involving the second fundamental form. You've got a del P NQ and then an HPA HQB projecting it into the surface sigma. So this collection of stuff, that and that, gives you the second fundamental form. And what you'll end up with is, from this first term, minus or plus, actually I probably shouldn't, I just about managed to write that low, KAB, from that, that and that. Then there's an HCY, del X, Vy. From this term, it's much the same. You've got del P NR projected with HAP HRC, so that's going to give me KAC. So I get minus or plus KAC HXB del X Vy and an NY from here. I think I have left out an NX going from here to here. That looks better. And then I end up with this last term here, plus HAP HBX HCY del P del X Vy. And then I subtract off the same things with A and B swapped round. So, what we have discovered is that 3R ABCD minus VD is equal to this stuff. The next thing to do is that there is one term that obviously cancels. I'm going to subtract off these three terms with A and B swapped round, so it is kind of obvious that here, because this thing has a KAB sitting all on its own, and all the things in here are dummy indices, that will cancel. So symmetry will cancel this term together with the first one of that. So I'm going to be left with the following collection of stuff. Minus or plus KAC HBX NY del X of Vy. And then I subtract off the same thing with A and B swapped round, so that's plus or minus K B C H A X NY del X of Vy. Then I have this term here. This is plus HAP HBX HCY del P del X Vy minus HPB HAX HCY del P del X Vy. Now, at first sight, this looks terrible. How can we manage something involving a Riemann tensor out of this? Because this involves derivatives of the metric field. The answer is, of course, the derivatives of this metric field are a little bit fake. Here, What have we really got? You've got ny del x vy. That's the only first derivative terms you've got here as well. Well, of course, the easiest way to figure out what that is just to take the derivative of ny vy. That you already know to be 0 because v lies in the surface sigma. That contains two terms. The first is ny del x vy, which is what we want. And the second is plus vy del x ny, which we know something about, because this thing is just the derivative of the unit normal, and therefore we can always write this in terms of the acceleration and the second fundamental form. So the trick is to use that to simplify these two terms. So what you get is that 3 are a, b, c, d, vd is equal to. Well, since this is 0, that thing is minus that thing, so you end up with plus or minus k, a, c, h, bx, and then you have ny del x vy, turns itself into a vy del x ny. Then you have the same thing with a and b swapped round, opposite sign. So you get minus or plus k, b, c, h, a, x, v, y del x of ny. Now it's these two terms. These two terms, you can just use the Ricci identity to get rid of these second derivatives. Here you have a collection of stuff with a and b in that order. Here, I've swapped round a and b. But that's, of course, the same thing as swapping around x and p. But swapping around x and p just basically tells you commute these derivatives. So the last two terms are best written plus hap hbx hcy times del p del x minus del x del p acting on the vector field vy. And now you can use the Ricci identity and get something which is linear in v. So, I hope I can erase this collection of stuff. Three are a, b, c, d. Vd is equal to. Let's look at this term first. This would be r, p, x, y, z, I suppose. P. Actually, the simplest thing to do is to make the last index a d so that it corresponds to the thing we've got up there. And then there's a projection of HAP, H, B, X, H, C, Y. In other words, this term looks like the three-dimensional Riemann tensor is more or less the same thing as the projection of the four-dimensional Riemann tensor into the surface. But there are some correction terms. Plus or minus K, A, C, and then this collection of stuff. That is, to all intents and purposes, the second fundamental form again. I've got an HBX, so this is going to kill off the acceleration term, and you end up with K, B, Y Vy. From here, this is, again, basically the same thing as KAB, because the acceleration term will be killed off by that h, and so you get minus or plus KBC KA Y Vy. This is true for arbitrary vector fields sitting in sigma. Those we call Vy, which have the property that Vy can be written in the form HY dVd. And now we can reconstruct the whole lot. 3R A B C D Vd is equal to the projection of all of these things so all I have, let me see. What I've written is correct, but not exactly what I really wanted to write. That's what I wanted to write. Plus or minus the same thing as KAC, KB, let's leave it like this, VZ. Or plus KBC, KA, ZVZ. Since that is true for all vector fields in V, the tensor is 3RABCD is equal to the projection of all of these things into the surface plus or minus KAC KBZ minus or plus KBC KAZ. There's something that looks funny about this. This should be a D. That looks better. And the only place that's gone wrong is here, which I didn't mean at all. This is P, X, Y, Z. That's a formula for the three-dimensional Riemann tensor in terms of the four-dimensional Riemann tensor. This equation is sometimes called the Gauss equation. So it tells you about the curvature of this surface here in terms of the curvature of the space-time in which it is sitting and K, which tells you about how the surface is embedded in the space-time. So this is a deep and useful result. Now, I don't know how many of you are going to the higher dimensions supersymmetry course, probably lots. If so, you've undoubtedly discovered about brane worlds. This is the fundamental equation which governs how brane worlds behave, although in that case it will be dimension 5 to dimension 4. You haven't actually got to that yet. You haven't? Oh well, it'll be easier to understand when you get there. Let us record on this board for posterity this equation. Although I used 3 and 4, of course, you notice that there was nothing terribly important about the dimension here. Let's simplify things a little bit. You will notice that this collection of stuff here has the symmetries you'd expect for a Riemann tensor. Sometimes something which is quite useful that is a consequence of this equation you can think of as being contracted Gauss equations. And these you can use to describe the Ricci tensor of this surface and the Ricci scalar of that surface in terms of higher order things. So step one, let's contract this with GAC. So on the left hand side you would have GAC 3R ABCD is equal to HAP, HBQ, HCR, HDS, GAC, RPQRS, plus or minus GAC, KACKBD, minus or plus GAC, KBC, KAD. So the left-hand side, on the face of it, looks like a mess. But of course, if you write GAC as HAC minus or plus, sorry, plus or minus, I wrote it right but said it wrong, ABCD. This object lies entirely in sigma. So if you dot any of these indices on the Riemann tensor with an n, you'll get nothing. So contracting with GAC is the same thing as contracting with HAC. That means you can regard this thing as being the three-dimensional Ricci tensor, RBD, because these terms don't give you anything. Here you have GAC, HAP, HCR, which is of course just the same thing as HPR. So that term is a mess. Plus or minus. GAC, KAC, I will generally call just a big K. This term is a mess, because it just contracts that index with that index. So what I end up with there is, of course, some expression for the Ricci tensor in terms of the second fundamental form and the higher dimensional Riemann tensor. So as a piece of notation, K is sometimes called the trace of the second fundamental form. And of course, this thing we wrote as GAC, KAC, but that's obviously the same thing as HAC, KAC, because HAC is related to G, like that, but that's not like that, it's like that, KAC. But these unit normals dotted with N, dotted with K, never give you anything, so this is the same as HAC, KAC. Sometimes one way of calculating it is easier than the other. So here is a nice formula for the Ricci tensor. So, in terms of what happens in brain world models, which we're not going to consider, but you could just see the consequences of this. If you're interested in saying that the Einstein equations must hold for this, and you were trying to model this surface as our universe, then it's related to what goes on in the larger space-time, how that surface is embedded. Or alternatively, you can regard this as a Ricci tensor of space by making sigma to be a surface of t equals constant, in which case this tells you how the curvature of the surface is related to the curvature of the big surfaces. It's got, as I say, zillions of applications everywhere. Lastly, it's very useful to have a formula for the Ricci scalar. This is actually much more useful in practice because it's usually easier to deal with actions and field equations. And so we can calculate that. That's going to be just HAB so I'm going to define it that way. Seems completely reasonable. That is from the equation that we have sitting over there, HAB. HPR, HA QHBSR PQRS plus or minus K KABHAB minus or plus K ACKCBHAB. A moment's thought will reveal that this thing is HAB, HAQ, HAS, same thing as HQS. Then from here we get plus or minus what gives you trace k squared, and this is minus or plus, well, just rearrange it, KAB, KAB. At first sight this looks bad, but now you can replace H by G minus or plus N, and you'll see that it becomes nice. So what do you get from all of that? GPR times GQS times RPQRS is the four-dimensional Ricci scalar. Then you have two terms which involve NP, NR, GQS. And then the other one is what? GPRNQNS. Then there's a term which involves NP, NQ, NR, NS, which is of course symmetric interchange of PQRS, dotted with this thing, interchange of lots of those things. So that gives you absolute. These two terms are of course the same. Here I contract on index 2 and 4 to give me a Ricci tensor with index P and R. Here the same thing, I contract on P and R, I get QS, but then the two terms are the same. So this is equal to R minus or plus 2 N P N R R P R minus or plus, no, plus or minus K squared minus or plus KAB. KAB. So that is the last of the Gauss equations. 3R is equal to 4R. Minus or plus 2 NPNR RPR. Plus or minus K squared minus or plus KAB KAB. There is another way in which you can think about this. We describe these as determining what the three-dimensional curvature is. But you can actually regard this the other way around. You fix 3R and know the K's. This determines the projection of the four-dimensional Riemann tensor into the surface. This determines what happens when you project the normal components of the Ricci tensor into the surface, and, well, that's basically it. That might make you wonder whether there's some other formulae like this that you could derive in different ways.
I'm given an n-dimensional Riemann tensor and a couple of symmetric 2 tensor, 0-2 tensors. Can I get, or 1-0-2 tensor, can I determine whether or not I can envision my n-dimensional manifold as being embedded in an n+1 dimensional manifold with it?
You mean, let me translate this question. Given this stuff, abstractly on its own, I figure out whether or not I can embed that in dimension 4.
Yeah.
Well, in one higher dimension.
Yeah.
Okay, here the answer is tricky. The answer is that you can if the geometry is Riemannian, so that the signature of the metric is always positive definite, the answer is that you can always locally do it in dimension n+1. If how it is Lorentzian...
Yeah, but these are tensor things, so locally is not sufficient.
I agree. Okay. If it was a local question and you had one minus sign in the metric, so you call it Lorentz geometry, the answer is 2n+1. This used to be an exciting topic years ago. I guess it's probably as exciting to some now as well.
Okay. And one more random question. Is this necessarily, have we somehow made use of the fact that we're talking about a metric connection, or is it a point?
Yes, we have definitely used that. We've used the symmetries of the Riemann tensor extensively in this calculation. Okay. In its most recent incarnation, when we said, for example, that this was equal to this, we used the fact it was a symmetric metric connection. Because if it wasn't, the first pair of indices and the second pair of indices are different. Tempted to say we've used the cyclic identity as well, at the point at which we said dotting the Riemann tensor with 4 n's.
Sure.
Well, actually that's not true, because 4 n's will always give you 0, even if you're not. We've also used the fact that you can commute g with the derivative operator. Pretty bad, but if you're just interested in torsion, that won't be the end of the world. You could invent formulae like this, including torsion, if you wanted to. I would not attempt to invent this lacking metricity. Okay. I think that would be horrible. So the next question is, are there any other equations like this describing the behavior of surfaces? The answer is yes. They're usually known as the Codazzi equations. Oh, for the Riemannian case, I'm pretty sure it's globally n plus 2.
Okay. That still doesn't answer whether or not, if I have the extra, 0, 2 tensor, that gives me an extra condition.
Yes, I don't know the answer.
Okay.
Probably someone does, but I don't. So the Codazzi equations, well, if I was interested in building, say, 4R, I would need to know this object, I would need to know this object, and then I'd need to know something that had one leg in the surface and one leg perpendicular to the surface. I don't know of a nice way of doing this except backwards, so to speak. So I'm going to contemplate just taking the three-dimensional covariant derivative of things like k. Well, this thing, if you think about it, is of course the same thing as HCB del B of k. And this thing is equal to HCB del B of HAD del A of ND. Then I want to contemplate this object, 3 del A K C A. This is equal to, well, again, it's not so hard to do. You basically take the three covariant derivative of k, that's a 3-indexed object, and then do some contractions. So what I did was to do I can't read my writing, HAF, that will work, HCE, HAG, del F of K, CG. No, GE, that's the right way around. G, that's that one with that one, E. That's what I mean. And now substitute in for K. Do I call it X? So I end up with that expression. And now I just take the difference of the two. So if you were systematically exploring all formulae, you'd find that quite quickly. What you would not find is that the difference between the two is nice. So you have this expression is a difference between the two, and you just write out what you've got here. In actual fact, we want to make one simplification. So I wrote this down using the fact that it was really 3 del acting on something, so I have 3 indices. But you see here I got an HAF, HAG, so I can turn it to an HFG. So I will do that, and you will get HFG, HEC del F of KGE. What am I talking about? It's nonsense. It's not what I wanted to write down. Well, it's not nonsense, it's just not what I wanted to write down. I want to do this in terms of the H's. H, X, G, H, E, Y, del Y of NX. And now what I want to do is to subtract off this thing, which is HCB del B of HAD del A of ND.
You mean, is that supposed to be a C on the left-hand side?
A C on the left-hand side.
Yeah, it's A is summed over, on the left-hand side A is summed over, whereas A is re-indexed and summed over.
here. Yes, that should be a C, as it was up there. Now you just multiply all this stuff out. At first sight, this looks horribly complicated, but here we've got h del f hgx. But this is effectively the same thing as the three-dimensional covariant derivative of h, and so since it's a metric connection, we can forget the derivatives of h and rewrite this as hxg goes with hgf, giving me an hfx. HEC-HYE is HCY. And then del F, del Y, NX. Minus the same thing, HBC, HAD, del B, del A, ND. There's something terribly wrong with my indices here. Isn't there? No, maybe not. B, A, D, C, F, no, that's fine. Now, what I want to do is to realize that this is in fact a commutator. So the thing to do is to rewrite everything using the same notation, which of course is always hard. HCY del F del Y of NX minus, let's rewrite this thing. We would like to call this D and X. And we'd like to have it upstairs, which means that the H here has got an argument which is an X. The H here has got an argument that is a C, like it or not. And let's see. This thing here, I would like to call F. If I call that one F, that one is an F. So I have an F there and an F there. Here I would call this thing a Y, which means that that would be a Y. Miraculously, this is the same as this. Now I can Ricci identity and get H, X, F, H, C, Y, R, F, Y, X, Z, N, Z. Now, Y, X, Z, Y, F. Something has gone wrong.
Did you really want the, maybe you wanted the X lower in the first one instead of the X raised?
Well, that solves the problem. Almost certainly. Does look a little bit better. Let's rewrite that as GFX minus or plus NF NX HCY R F Y X Z N Z. Yes, that's what I wanted. The tensor is antisymmetric on its last two indices, x and z, but here we have an nx nz, so that term doesn't contribute. Gfx contracted with fx on the Riemann tensor gives me the G tensor, so this whole thing is equal to h, y, c, r, y, z, n, z. So this thing is, as promised, the projection of the Ricci tensor into one direction normal to the surface and one direction lying in the surface. So the Codazzi equation we can record here, del 3 a k c a minus 3 del c of k is equal to h c y r y z nz. And that's all you're going to get that's useful. These are collectively known as the Gauss-Codazzi equations. No, none of them are too terrible if you add. I don't want to work them out though. There are some generalizations of this. You can generalize this to p-dimensional surfaces sitting in q-dimensional space, in which case the difference is that instead of having one unit normal to the surface, you have many unit normals perpendicular to the surface, and so you have to deal with that particular thing. So that makes it rather more complicated. For our purposes, we only need to do the case where the surface is one-dimensional lower. So typically you want to think of this as a way of splitting up into space and time, but of course it works under much wider set of circumstances. Given the time, we should probably stop there.